Please see page 523 in the 6th edition of Brucey to see where this question was derived from. Which of the following compounds has the lowest carbonyl stretching frequency? Now, carbonyl group is a C double bond O. And as far as stretching goes, on the IR, the frequency at which bonds stretch is going to decrease as you go from left to right. And frequency is proportional to another concept called wave numbers. And wave numbers are given as centimeters to the -1. Those are reciprocal centimeters. Now, in order to get the lowest stretching frequency, we want to observe where other bonds come in. So triple bonds stretch at the highest frequency, and then double bonds, and then single bonds. So we'd like to find a carbonyl which is going to have partial single bond character. And in order to get partial single bond character, we need to have delocalization. Now, to get delocalization, you need to have sp2 atoms in a row, at least 3 or more. 1, 2, 3, and 4. sp2 atoms in a row will do it. Over here, we've got sp2, 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 but as you can see here, there is an sp3, so that will not be delocalized, and so we're going to rule out number 1. As far as number 3 goes, it's the same idea. We have an sp3 here, and of course, as far as number 4 goes, there are only 2 sp2 carbons. You require 3 or more to have delocalization. Now, what's actually going on here? Well, let me show you what the deal is by drawing some resonance structures. So what I'll do is, I will just draw a regular old ketone like this. Now, when I do resonance for this ketone over here, what will happen is the only resonance structure it has is going to be one in which we put a negative charge on the oxygen. And so what we'll end up getting here is a oxygen here with a negative charge, and we'll have a positive charge over there. So there's only 2 resonance forms. However, I can draw structures that are going to be delocalized, such as this. And when you have a delocalized system, you have additional resonance forms. Now, the book only draws 2, but there's actually 3, so I'll draw them out so that I can explain this. So in the first structure over here, we get an O with a minus over there, and then a positive over here, and then a lone pair, a double bond like that. But then we get to take it a step further, and we go ahead and we bring these electrons in like that, and we get an additional resonance form, which is going to have the oxygen with a negative over here, and a double bond there, and a positive charge over there. So, the idea is that for this regular old ketone that we see above, we only have one resonance form that has a partial single bond character. But when we have the delocalized system here, we in fact have 2 of them, and therefore this form, the conjugated form, is going to have more single bond character, which means that if you have more single bond character, the frequency of your oscillation will be lower, and that's the reason why answer choice 2, answer B, is the correct answer. Okay, but there's more. I believe he can take a question from the next page, which is 524. So I want to show you how that works right now, because I think it's a very likely question. So what I'll do here is I'm going to draw here a molecule that's called an ester. So here we have an ester, and right below that I'm going to draw a molecule which is called an amide. And so there is the amide. In this case, I'm only going to draw 2 resonance structures, lone pair like this, and that pops up, lone pair like this, and that pops up, and I know you can hardly wait to see what we're going to get. I'm pretty excited about it too. So here you get a O with a negative charge like that, and then a double bond here, and then an R, and just to really emphasize it, there'll be a positive there on the oxygen. We know that's a bad thing because oxygen is electronegative, so we don't want to see that. And then over here what we have is we have a double bond on the nitrogen, and then we have the positive charge on it. Now, if we look at the location of the absorption of each of these on the IR, we see the ester is going to come in at 1740 wave numbers. And we'll see that the amide is going to come in around 1670 wave numbers. So the question is, how can we explain this? Well, it turns out the explanation is going to involve two separate issues. One is resonance and the other is induction. What happens with the ester is the positive charge on the oxygen is such a terrible, horrible, awful thing that this resonance form here becomes relatively insignificant. Therefore, the carbonyl is going to have a lot of double bond character. Even though the oxygen is so electronegative, it effectively does not remove very much electron density. And that's why the frequency is going to be a large number. The wave number is going to be a large number. So what we're seeing here is, in the case of the ester, we're seeing that resonance is going to win. Resonance wins. But what happens in the case of the amide right over here is that we've got to have to take into consideration, I'm looking for a cool color, I'll go with red on this, I haven't used it. We have to take into consideration that a positive on nitrogen is not really as bad as a positive on oxygen. So in this case, what happens is that you've got a situation where this resonance form is actually more significant in comparison to this one, okay, when we look at which one will be more significant or important. And in addition, the nitrogen is going to inductively, because of electronegativity, is going to inductively remove more electron density. So the less electron density that's going to be in the carbonyl, the more the frequency is going to decrease. So the more single bond character and the less electron density, the lower the frequency is going to be. So that's the deal, okay? Cool beans.